So we're going to be continuing on into the final part of chapter 7. We're going to be working on simplifying things, and I know the first thing you're saying is, oh, there's a negative under the square root, that can't happen. Well, in this lesson, we are learning what it means when that happens. Then we're going to work on doing our arithmetic with what we call powers of I. So the hard and fast rule has always been that when you get the square root of a negative number, you say no solution. In this lesson, there is something we actually do, and it's called an imaginary unit I. Why is it imaginary? Well, because the square root of negative 1 doesn't really exist in arithmetic. However, we do encounter it when we work with circuits and other special scenarios, especially the ones that are related to physics. So sometimes the math might work out where there's a negative under the square root, but we can still set up a system of circuits to handle power. So what we had to do was come up with something to say, okay, let me combine all these quantities that I'm getting the negative under the square root for, and I'm going to make this value represent it so that I'm not looking at that negative value under the root. Because it does happen in the calculations, but the real world is still functioning even though there's an I in the answer. We're still seeing a phenomena happen. So the square root of negative b would be I times the square root of b. So the I is the square root of negative 1, but it's kind of like you're factoring that I out. So now I can actually look at that and do some algebra or some math with it. So the square root of 25 negative would be I square root of 25. In b, the negative would hang out front, and I would get negative I square root of 81. Well, 81 reduces. So again, once we get that I, we can actually start doing things with what's left under the radical. So this is how we have addressed how the real world is different from our perfect math world. There's nothing more I can do to 7, so it just hangs out as 7. 44, is it divisible by something? Yeah, it's divisible by 4. So I can simplify that to 2I. So really in this unit, there's nothing that's new. It's just learning that we can take care of that negative number and actually do calculations now. So this would be I times I. Then I'm going to take the square root of 16, which is 4, square root of 25, which is 5. I'm going to multiply those together. Now, I times I is I squared, and this is where you have to remember. I squared is negative 1. So it becomes negative 20. So let's look at B. I have an I in front of each. I can do nothing further with 6 or 5, but I can do something with I times I. That's I squared, which is negative 1. And I'm not really going to write that as negative 1 times square root of 30. I'm going to write that as negative square root of 30. So in the lab, the key thing here is to make sure that you're fully reducing that root and you're doing all that arithmetic that we learned to do with the root, just with that I taken out front. Now here in C, I do have 2 negative numbers under the root, but when I multiply those 2 roots, I'm going to get the I squared in front. I'm going to get 48, which reduces to negative 4 square root of 3. Now, of course, someone's going to say, well, couldn't I have just done negative 8 times negative 6 is positive 48? Well, the problem with that is you miss that I squared, and then your final answer has the wrong sign. So if there's a negative under the radical, the very first thing you need to do is address the I. Once you've addressed the I, then you can move forward with that arithmetic. But if there's a negative under the root, you've got to pull the I out. So just like here on the next one, I've got to pull that I out first, then I can do 5 times 7. This is not able to break down. That's my final answer. The same thing happens here. We have to address the I first. Now the I's in this case will cancel out, and I'm left with 80 over 5, which would be 80 divided by 5, which is 16, which is 4. So the I's don't always cancel out. And then B, the first thing I've got to do is address the I. Then I can look at 40 over 10, which is 4, which is 2. So now we're going to take a look at the complex numbers. Complex numbers are going to be numbers that involve I, but also involve a constant a. So like 2 plus 2i would be a complex number. And it's complex because A is a real number and B is considered an imaginary number. For any complex number, we're just stating that, hey, A is a real number, B is going to be a constant from 0 up, and we prefer to write them as A plus BI. So this becomes the question. I get this from students all the time. If I just have 3i, is that a complex number because I can write it as 0 plus 3i? The answer is no. If a is 0, we just call that a pure imaginary number. So that's going to be different than if I just had 2 plus 3i. So 3i does not count as a complex number. And we consider standard form to be a plus bi, which is addition. So that's going to be really important in the lab, so that addition has to happen. So here is just some ways that I can do things with complex numbers and my number groups. It's really helpful. I would suggest copying this down on a sheet of paper so you've got it in front of you as you work in the lab. Occasionally you'll see a question about, is this a rational number? Is it a rational number? Is this an integer? Is it not an integer? So when I have a situation where b is equal to 0, that means this is just the term a. So that means b is equal to 0, so that imaginary term doesn't exist. So then it's irrational or rational. If it's rational, it could be an integer or a non-integer. In the top, if I have an a plus bi, like 2 plus 3i, it's considered a non-real complex number. There's no further breakdown you can do besides saying, hey, this is a complex number, and it's also non-real. So we're just going to be adding and subtracting, guys. This is just like terms. It's like terms is all this is. So I'm going to add these together. I can combine the -1 and the 9. I can combine the 8 and the 3 because they have a like term I, and I get 8 minus 11i. It's just like dealing with an x unless you start multiplying and getting I squareds. So in part B, I can drop the parentheses. I can group all my terms together. So I have a -3, a 1, a -7. I'm combining all of those together. I have a 2, a -3, a -5. I'm combining all of those together to combine my like terms, and I get -9 minus 6i. This is just like combining like terms with x's. Now in part A and B and C, I now have to distribute the negative. So before, I could just drop those parentheses off. Now I have to distribute that negative. So when I distribute the negative, this becomes -4 and -i, which is why this says -4 here, and this says -1 here. I'm just grouping those terms together. Same thing happens in B. That's -12, positive 3i, because minus a negative is plus a positive. I group my terms together. I combine my like terms. And then in part C, I'm going to group my terms together after I distribute that negative through, and I'm going to get 0 minus 4i. Remember, that's just a pure imaginary number. It is not going to be considered complex. When we multiply, this is where we really see the difference in the arithmetic happening. So here, I need to distribute 6i to each term. When I do that, I'm going to have 6i times 3i, which is going to give me 18i squared. 6i times 4 is 24i, but I know that I squared is -1. So I have to convert that over. If you enter I squared into the lab, it's going to be wrong. So this would be -18 plus 24i. Why did I write it that way? Because they want you to write this a plus bi. So you have to write the constant in the front, and the back needs to have your b value and your I value. Here I'm going to FOIL. So the first thing I need to do is FOIL and do first times first, outer, inner, last. Once I get that situation going on, then I can work on looking at first, outer, inner, last, and combining those little terms. So I'm going to complete that multiplication, and I see, oh, I can combine 24 and -8, And I also know that I squared is -1. So notice how I'm plugging in those -1s in parentheses. That's to help you do that arithmetic. Once you do that arithmetic, then it's fine to work with the negative values. Then I can combine the 12 and the 16 to get 28. Here, I'm going to FOIL again, and then I'm going to look at, okay, what is my arithmetic here? I'm going to complete the multiplication, and I'm going to say, okay, I have 12i and 6i. I can combine those. I know I squared is -1. I want to have it in a plus bi format. Now we're going to have the sum and difference of squares. This is that formula back from elementary algebra. However, complex numbers don't necessarily follow the pattern of a squared minus b squared because you're going to get an I squared in that last term, and that's going to make it positive. So this is a shortcut, okay? Shortcut. When you see the conjugate, you could just do a squared plus b squared because if you FOIL it out, the middle term will cancel and the I squared is going to change that sign. Now I'm looking at dividing. This is tricky, right? I can't just do 23 divided by 3 and I divided by I. That is not accurate. I'm going to have to use a conjugate. So here's the rule for this, guys. Imaginary numbers follow a radical form. You have to rationalize the denominator, meaning you cannot have an imaginary number in the denominator for your answer to be a final answer. So we can use that handy shortcut because in the bottom I'm multiplying by the conjugate, so it's going to be 3 squared plus 1 squared, which is just 1 because I'm getting it from the previous slide. It would be your a squared plus b, which is the number in front of I. Then I'm going to combine my like terms. I'm going to say at this point, okay, is there anything that every term can be divided by? Yes, every term can be divided by 10, which gives me 7 plus 2i. Remember, you do not have to show the step of factoring out. You could just be right here and say, cancel, cancel, cancel. Everyone divided by 10 is 7 plus 2i. So here, what is the conjugate? Well, the conjugate of I isn't a thing, right? It's just multiplying by I to rationalize the denominator, or negative I, because if I factor by I, I'm still going to get a -1 in the bottom. So the reason they did negative I was to take care of that negative in the denominator and to get a +1. You could just multiply by I over I. That is okay. And then you'll just get a -1 in the denominator to adjust. So then I want to write it in a plus bi form, but I have -1 minus 5i. I mean, I might could write -1 plus -5i. I think the lab would still take that. But in general, when the first and the second term are negative, you can leave it as subtraction. So we can take I out a little further. I cubed, which is going to be I times I squared, which is -I. I to the 4th is 1. I to the 5th is I. I to the 6th, oh, -1. I start a pattern. And I have that pattern continuing. So I'm going to find the powers of I. Notice these are all really big, but I'm going to use this information. So to find I to the 28th, I want to write that as a power that's in my table, okay? So I want to write it as 3, 4, 5, 6, 7, or 8, or 2. So I say, okay, 28 is divisible by 4. So it's going to be I to the 4th to the 7th power. I to the 4th is 1. 1 to the 7th power is 1. If you did I to the 7th times 4 raised to the 4th, you could just go here, and we know I to the 7th is -I raised to the 4th power would be positive. So you could work with it that way, but generally we want to put the smaller term in the parentheses. So 19 is 16 times 3. Well, we already know what I to the 3rd is. But I want to write I to the 16th as a power in my table. And generally, I want to use those 1 powers, okay? That's typically where I want to be at, is these 1 values whenever possible. So I can write that as 1 to the 4th times negative I, which is negative I. I want to take care of that negative exponent first. I to the 9th would be I cubed, or it could be I to the 8th times 1. So either way, you would still get to your answer, okay? Either way. This can be tricky to know how to do the powers, guys. And while the slide is showing one way to get there, as I'm talking, you can hear me saying there are other ways to get there. So I to the negative 22, got to get rid of that first. Then I'm going to think, okay, powers of 22. Well, I know that I squared is negative 1. I to the 4th is going to be 1. So is there any way I can write 22 to the 4th? Is there any way I could write, I can't write 22 to the 4th, but I could do 20 times I squared, which lets me do to the 4th power. So really what you're trying to do is get it to a 4th power, a squared, any of those actual number values is what's happening here. I to the 4th is 1. 1 to the 5th is just 1 times negative 1, which is negative 1. So that's really what you're trying to do with those powers of I, is again, I want to use, whenever possible, this one, I to the 6th, I to the 4th, I squared. That's what you want to try and rewrite those powers as.